Yeah, so in this video, we are going to talk about few of the foundational aspects of geoinformatics, satellite data, and this information is quite relevant there. Okay, so I'm a data scientist who recently started working with satellite data. At first, it was challenging because previously I did not explore this aspect much. So, to make my life easier, what I thought that regularly, I will learn a few things, the basics, and certain other nuances related to this field. And gradually, I will start recording those videos and keep them well documented on my YouTube channel. So, this is the first video I'm making. So, in this video, it's not planned on how to, you know, properly chronologically cover everything. Rather, it's a randomly picked topic. So in this video, first, let's talk about the shape of Earth. Now, this is from the perspective of a data scientist who wants to use satellite data to do some kind of an analysis, find some insights. So I'm not going into the details like physics based details of the shape of Earth. Okay. So now let's imagine that our world is made up of only water, okay, and there's no land anywhere. Now if you think so, let's remove the waves, the winds and tides, okay, and only let gravity and earth's rotation act on the water. If that is the case, then whatever the water surface naturally takes a shape with some bumps and depressions caused by the variation in Earth's gravity. This is nothing but the geoid. Now, this surface is specific equipotential surface of Earth's gravity field. सीधा मतलब basically it means that anywhere or at any point on this surface, it will have the same gravitational potential. Okay, so why is it so important? Okay, why do we even have to look at this ugly face of our Earth? The reason being that if we want to measure height, let's say we want to measure what is the height of a building or what is the height of this mountain, we always extend this calculation from the mean sea level, right? So basically, the mean sea level is a zero, the zeroth point from where we start the calculation. To find this mean sea level, which is our reference in this case, this equipotential surface becomes the mean sea level. So the geoid corresponds to mean sea level. And now, in reality, not the whole of Earth is covered by water. So, what happens um, on land? So, basically, mathematically, we extend this surface beneath the continents. Okay, so this is the basic idea. Now, as you can see, I've already written a few things about it. So, it says it is the wavy, irregular structure that approximates the mean sea level under the influence of gravity and rotation, extending through land and ocean rather than being a perfect sphere or simple ellipsoid. That's okay. But then you can read about this. Then comes this part, ellipsoid. So, why do we need ellipsoid? Now, imagine that we have to do some mathematical calculations. For example, we need to calculate GPS coordinates, we need to calculate distance between 2 points, or the area of a landmass. These things require mathematical operations, and to basically do them on a lumpy potato shaped geoid is it's very difficult. That is why scientists approximated the shape of the earth, and we call this approximation as ellipsoid shape. So this is a smooth mathematical approximation of the earth that is squished at the poles and it bulges at the equator. So now let's talk about datum. So what is datum? So datum is the ellipsoidal shape of Earth plus an anchor point. Now we come across a new word called anchor, or rather a term called anchor point. So we'll talk about this, no issues. So before the satellite technologies mature phase, for example, before 1950s, countries used local datum, and this was designed to fit only their specific needs. And they honestly never cared about the precision globally, rather than they cared about local precision. So let's take the example of India. Okay. Now, India followed a datum called the Everest datum. Okay. This is the Everest datum. And in Everest datum, the anchor point was at a place called Kalyanpur in Madhya Pradesh. So I will just refer it as Madhya Pradesh. Okay. Now, why there? Because if let's imagine this to be our India, and this is the actual shape of the Earth, and this is the ellipsoidal approximation. Now, at this point here, scientists believed that this is, and by the way, this is actually Madhya Pradesh. Okay. So at this point, scientists believed that the surface, actual surface of Madhya Pradesh, and the ellipsoidal surface, they kiss each other. I would use this word, kiss each other at this point. And this is the best point to say that, okay, if I start my calculations from here, then if this is India, and this is the northern side, this is the southern side, this is the western, and this is the eastern side, and if I make, or if I imagine that the ellipsoid and the actual surface of Earth kisses somewhere in between all these points, and at the middle of this country, then error which goes, or which starts to propagate as we move towards the north, the error which starts to propagate as we move towards the south, the error which starts to propagate as we move towards east and west, they balance each other. So this is something we need to understand here. As a result, they pinned it in Madhya Pradesh, and maybe not in Assam or not in Mumbai. I'm just saying, giving you an example. Now, imagine 1984. Okay. So in 1984, when satellite technology came along and it matured itself, then what happened? We actually understood where the Earth's center of mass is. This thing, very carefully. So we actually understood where the Earth's center of mass is, and that center of mass was considered the actual center of the ellipsoid. Now, every country were using their own logic of making the ellipsoid and deciding the anchor point wherever they felt suitable for their own needs. But based on the WGS-84 global datum, it was decided that the center of the Earth will be considered the anchor point for WGS-84 datum. And if we do the calculation today, we will see that there is a 295 meters, basically 295 meters, I would say, shift, or basically an offset between the true center of the Earth, that is a geocenter of the Earth, and the ellipsoid that was imagined using the Everest datum. So this is how a confusion was brewing between multiple local datums. Finally, it got resolved when a global datum was made available. Now let's talk about two different ways in which a point in three-dimensional space can be identified, okay, or can be defined rather. First is called geodetic system, another is called geocentric. Okay, So let's go one by one. Geodetic system is basically the system where two angles and one distance based coordinate is used. So the latitude and longitude are the two angle based coordinates, and one is the height. This is a distance or linear coordinate we use. Using these three, we pinpoint any location. Okay, this is how we pinpoint any point on a three-dimensional space. In case of geocentric system, this is more or less like how we imagine that the earth is inside a giant three-dimensional box, and let's say the center of the earth has the coordinate 0 0 and 0, and there are three axes x, y and z. The x axis originates, all the axes originate from the origin. The x axis comes out of the point which is the intersection of the Greenwich meridian line and the equator line. Okay, so this point, and then 90 degrees east of this x you will find the y coming out of the equator and originating from the center. And when you have x and y defined, then you just draw 90-degree line that comes out of the pole. This will become your z axis. So these are the three axes, and this basically is purely mathematical, and it uses meters and not degrees. So one distinction between these two are it's in degrees and it's in meters. Now I'll come to the point where we talk that why there are two systems present. I'll come to that point shortly. So now let's address this problem, or not the problem, but this issue that why do we have these two systems available. Let's say any computer based calculation happens where the math is done in meters. Okay, and as the math is done in meters, we prefer geocentric systems there. Now when the results of those calculations are being shown to humans, humans prefer degrees over meters. Just imagine that if I say to somebody that from origin, my point of choice or the point that I want to refer is 4 million meters east, or 4 million meters, positive 4 million meters, then it will create a lot of confusion. That is why for humans to understand this, we use the latitudes and longitudes. That is a geodetic system. So let's take the example of the GPS. In case of GPS, the satellites, when they talk to each other, they actually use geocentric system because computers love math in meters. But when the same thing has to be shown to human beings and human beings have to infer from that, then latitudes and longitudes are used. So that is why these two systems of defining a point in any three-dimensional space is actively being used. Now what happened was, in Cold War, intercontinental ballistic missiles were being used. So earlier people were more concerned about how to define their own country's geometry in the best possible manner. But now they also need to know the geometries of their enemy countries or enemy nations. To resolve this issue, what they did, they thought of stopping the use of local datum and creating a global datum. Because otherwise, the problem was any missile that, let's say, country A shot towards a country B would land at hundreds of kilometers away from its target. So basically, war necessitated and facilitated the development of, or rather I would say expedited the development of a global datum. Then came WGS 84 datum, which we called as the World Geodetic System, that is WGS, of 1984. So this is a geocentric datum, and the origin of this datum is at 000. It is at Earth's actual center of mass, made from several satellite. So basically what happened, multiple satellites passed over the Earth multiple times, made multiple readings and multiple calculations were done, and ultimately a, I would say, best fit ellipsoid was made, which obviously has errors, but the overall rate of error throughout the globe was very minimal. So it was not made from the perspective of fitting the ellipsoid at a local space, rather from a global perspective it was made. Now a lot of work was already done based on the legacy system. So monuments, infrastructure like buildings, bridges, and etc. were already made using the local datum of the countries. Now that the world was shifting towards a global datum, there has to be some interoperability between this local and global datum. Otherwise, the old things will become redundant, and it's very expensive and tedious to again rebuild them based on the new global datum. So then came the concept of datum transformation. That how do you transform one datum into another, and vice versa. Let's say you have the coordinates of an old infrastructure project, and now you have to convert these coordinates into global datum. Both of them are angular, but their centers are shifted. So what do you do in that case? Simply what you'll do, first convert the input lat longs. Let's say the input is in Everest datum. You convert the lat longs into Cartesian XYZs. So basically angle to meters you make it. At that point, it's still Everest. In step 2, you apply datum shift. So basically, we knew that there is a shift between the Everest datum and the global datum, that is WGS-84. So just apply the delta x, delta y, delta z to these 3 coordinates. Once that is done, then convert again these coordinates back into lat longs, because after applying these deltas, it has already converted to WGS. Now just convert it back into angles. This conversion is called ECEF. ECEF stands for Earth Centered, Earth Fixed Transformation. And this is different from projection. So we will come to this point as well. So the word projection is different, and it should not be confused with transformation. That's the most important point here. Now let's talk about map projections. So first we need to understand the difference between a GCS and a PCS. GCS refers geographic coordinate system, and PCS refers to projected coordinate system. Whenever we want to define where we are on the curved surface using degrees, that is latitudes and longitudes, we use this one. And whenever we want to do the same thing but on a flat map using meters, we use the PCS. Okay, but here's a problem. How do you flatten a ball? Earth is a ball. How do you flatten it? You can't do it without some stretching, without tearing up its skin here and there, and without some kind of distortion. Now, some may use the cylindrical method, but it is more useful for countries which are at the equator. Similarly, for countries like the USA and the continents like Europe, conical is more beneficial because it touches at this particular position, and planar or azimuthal is more useful for polar region based countries. So no single map is perfect for the whole world. To resolve this issue, and out of military necessities, the UTM was invented, Universal Transverse Mercator. In this, what happened was that The skin of the earth was peeled into 60 different strips, each of 6 degrees. Only the poles are not considered, as you can see this bald spot. Transverse Mercator was used, that is basically a cylinder was wrapped around but from pole to pole like this. Next, what happened, that this is, I think is quite clear, that 60 divisions, each 6 degrees, 60 into 60, 360 degrees. Now the starting of the zones or numbering starts from the international date line for each zone. India falls mostly in zones like this from 42 till 47. Latitude limits 80 degree south and 84 degree north, as the poles get narrower and narrower as we move up, because the wedges become so narrow that the math breaks down at the poles. So that is why we don't consider them. By the way, the poles have their own separate system called a UPS, but we won't discuss about it. It's quite complex and not doesn't warrant a discussion here. Now let's look at the image. Okay. Now if we look at the image of one of the stripes, we see that at the very center we have its I would say the spinal cord of it. Okay, the central line of it. It's called the central meridian. And at the center we also have, like horizontally center, we also have the equator. But apart from our normal convention, the center of a zone is not zero. So let's say the value of equator is not zero, the central meridian is not zero. Because if I imagine this to be zero, then everything that comes towards the right hand side will be positive in distance, and everything that comes towards the left hand side will be negative. Similarly, everything that comes below the equator will be negative, everything that comes above equator will be positive. Negative values confuse calculations. That is why scientists came up with a solution that let's give the central positions huge positive values or numbers, so that even if we go towards the left or down, we will never encounter negative values. And this process is called false easting. False easting is providing basically this central meridian a value of 500,000, and false northing is basically providing the equator a value of 10, basically I don't know how to call it. I think it's 10 million. Yeah, correct. 10 million. So that's there. Now let's talk about one more thing. And this is the last thing that we are going to talk about here. Let's talk about scale. Now here understand that in case of UTM, when the cylinder is fitted, it is not that the diameter of the cylinder is equal to the diameter of the sphere. Rather, it is narrower or smaller than the diameter of the sphere. The reason is, I'll talk about it, like why does the cylinder cut the sphere? And it was a design choice. The reason being that let's imagine that once the cylinder cuts the sphere, we have this region coming out of the cylinder, and it's a choice because anything and let's say this C line here is the center of the stripe. Now if you understand carefully, if you try to understand carefully, this A line, A to B and D to E are the exact points on the surface of the earth that touch the cylinder. The C line is a line that comes out of the cylinder, and every other line is actually inside the cylinder. So which are the points that will have distance is the most accurate on the flat map in comparison to the spherical globe. These points will lie in this A to B line and D to E line. So the scale of distance mapping, that is the distance in map to the distance in ground, is 1 here. Okay. As we move inside the globe, or rather all points which lie inside the cylinder, there the distance in map is greater than the distance in ground, because we are stretching the map here. That is why scale is always more than 1. And in this position, scale is less than 1, because the distance in map is actually less than the distance in ground, because here you have to compress it. It is already outwards, so you have to compress it. That is why the scale is always less than 1, which is around 0.9996. As we design I would call it a system where at middle the scale decreases below 1 and on the outside it increases above 1, the overall error minimizes or balances out. This is the choice that the scientists made. So basically, at this point or region, all the earth is inside. Imagine that if it is folded, and to project it on a surface, a squished image is made. As you squish, distance is in map is less than distance in ground. Hence, the scale at the center is 0.9996, that is less than 1. Similarly, on the green region, that is on this region, the map needs to be stretched. So the distance on map is greater than the distance on ground. Hence, the scale is greater than 1. So with this, I conclude my video today. As we move ahead, we will keep posting more videos. Maybe I'll keep bringing more insights. Any mistake that I have made, or any realization that I will have later on, that oh, I made this mistake while explaining it, I'll clear those in the next videos. And with this, I'll keep on documenting all my knowledge onto YouTube for my future self and for anybody who's watching this video. So if you like it, please give it a thumbs up. You may comment in the comment section. You can share your knowledge. You can even point out any mistakes that I've made. So thanks for watching. I'll see you in the next video.